Hi guys, these are your guided notes, or at least day 1 of your guided notes for lesson 1 of the unit 4 on similarity. So you should be in your workbook. There's a page that corresponds with this, and it starts off with something that we've already used before in this class and you've used before in other classes, which is a ratio. A ratio is a comparison of two quantities. We don't usually think of it like that, but that's its official definition. The way we usually think of it is a ratio is a fraction. So sometimes you'll see it written as a number over a number, or you'll often see it written as a number and then a colon between them and then another number. Both are acceptable. Both are basically saying that it's the comparison of A to B. So let's say there were 10 juniors and 20 sophomores in this class. We could say the ratio of sophomores to juniors was 10 to 20. And I could use this for 10 to 20, this for 10 to 20, or this for 10 to 20. They all mean the same thing. But since a ratio is essentially a fraction, it's not acceptable to leave it like that. So the second thing on here is that every ratio must be reduced. All fractions are expected to be reduced, so all ratios are expected to be reduced. The main thing that gets people hung up on this, though, is when they go to reduce, they need to always make sure that, let's not say use, sorry. Let's say that you must be in the same units. Meaning, when I put 10 people to 20 people, it wasn't reduced. I should have reduced it to 1 to 2, but people to people is the same units. On this next example, though, I'm going to be talking about something that's in inches and something that's in feet. Those are not the same units. We will have to make sure we address that. So a scale model of a car is 4 inches long. The actual car is 15 feet long. I want the ratio of length of the model to length of the car. So what I want to point out, this said length of the model to length of the car. The order matters. They said model to car. So if I could put it in words. We don't usually do that. You could put a colon between them, which is fine. But since we're going to be reducing it, I'm going to go ahead and change that to the fraction version of it, model to car. So this is me just addressing this part here where you can set it up any old way, but as long as the order matters. I can't put car over model here. So it tells me that the model is 4 inches long. It tells me that the car is 15 feet long. If you just put the numbers in that fraction, 4 to 15, you're going to think, oh, awesome, that doesn't reduce. I'm done with the problem. But that's not the case. Ratios are not supposed to have units, because in my example up above, when I said 10 to 20, 10 people to 20 people, what happens when you have anything over itself? 5 over 5, 16 over 16, people over people. Those cancel. This would reduce to just a fraction with no unit. Here, 4 over 15 would have a unit. It's inches over feet, and so it's not reduced if those haven't canceled. So I need to think of a way to reduce inches over feet, and the way to do that is to do a conversion. So off to the side, I'm not doing a proportion here, just off to the side, I'm going to get rid of the feet. So instead of 15 feet, I would like to be in inches because that's what the numerator is in. So just like you convert in your science classes, I'm going to put that over 1 because any number can be put over 1. And I'm going to multiply by something so that feet cancels. If feet's at the top, I'm going to put feet at the bottom so it cancels. And that'll leave me in the unit of inches that I want. Since there are 12 inches in 1 foot, we can cancel our feet and then just multiply across, because again, this is a multiplication sign, not an equal sign. You are not cross multiplying and dividing here. You're just going to multiply numerators and denominators. 15 times 12. Ooh, I really should have brought a calculator with me. Sorry guys, give me a second. It's 180, I believe. And that would have the unit of inches. 1 times 1 is still 1, so it's technically over 1. I'm going to ignore that and just leave it as 180 inches. So that means that answer that I put earlier of 4 over 15, not reduced, not my answer. We're going to come back to this 4 over 15 that I started out with my work. Sorry, I'm trying to erase this. And I'm going to replace this. Instead of 15 feet, we just said that's the same thing as 180 inches. So I'm going to keep the 4 inches on top here. That stays the same. But now I'm going to go ahead and put the 180 inches. And what you see, inches over inches, hey, it cancels. But 4 over 180 also reduces. 4 divides into 180 45 times. So this, and your calculator would have given you that too if you know how to work the fraction feature. But we get 1 to 45 out of that. So the ratio of length of the model to length of the actual is 1 to 45. So that's one use of one use of ratios is just writing the fraction, making sure we're reducing, comparing two things. We often see them in proportions. This is a statement where two ratios are set equal. Now, if they're ratios, we can write them as fractions, like a over b equals c over d. Or you can write them with the colons in between. That's not super math friendly for what we'll end up doing with it, so we're not going to usually write it like that. But since those are both fractions, unless you're talking the slope of a line, we're not going to have 0 in the denominator. So the only thing here is noting that b and d are not 0. That's never going to come up in this class, but it is something that we should note to be completely correct. You also could have something called an extended proportion. An extended proportion is where it's kind of like your work if you were trying to reduce. It's just a bunch of ratios that are equal. So for example, if you just had, like if we didn't have this, if we just had 3 over 6, you could say, oh, that equals 1 over 2. But 1 over 2 could have also been what you got from 2 over 4. When I have a bunch of ratios equal, which is what we had before I scribbled it out, that's just an extended proportion. We're not really going to use that for much. So 2a is what should be familiar from this class. We've solved proportions before. We're going to keep solving proportions. So I have two fractions set equal. What I want to point out about this is not a conversion like what I just did above. When you have something over 7, you can undo it by multiplying by 7. So I'm going to cross multiply by this one. The main issue that comes up is this negative. Think of a slope. If we had a line with a slope of negative 1/2, we want a line to be going downward, which means you could go down 1 and right 2, or you could have gone up 1 and left 2. Meaning that negative could have been with the 1, or it could have been with the 2. As long as you don't put it with both, because that would make you go up and right, which is not on this line. As long as you don't put it with both, it's accurate. So this negative could be with the x, or it could be with the 35. Doesn't matter. Pick one. Personally, I'm going to pick to put it with the 35 because I don't like having my x's negative. It doesn't matter, but that's my choice. So I'm going to cross multiply. 7 times x is 7x. Negative 35 times 3, ooh, I'm really regretting not having this calculator, is 100, negative 105. And if I'm wrong, good for you for getting a calculator out. Pretty sure it's that. But what I want to point out, main issue I see with solving these types of proportions is people think that they're going to get a fraction right away. You have to put an equal sign between it. You are still solving an equation. You have to then ask yourself, how do I solve the equation that's left? For this particular problem, it's really easy. We almost have x by itself. It's just the 7 that's the problem. So I'm going to divide by 7. So negative 105 divided by 7 goes in 15 times, I think. I believe I'm getting negative 15. Again, really should have had a calculator before I started doing this. My bad. But that would be our solution to solving this proportion. One other issue that can come up with solving a proportion occurs in part B. When you do 3 times x, no problem, you get 3x. But the thing lots of students forget is you are taking this 2 and you are multiplying it not just to the x. You cannot write this. That means I just did 2 times x. I need to do 2 times that entire x plus 1, which means I need parentheses. So we're going to end up distributing. And before I do that, though, I'm going to remind you that we have to have an equal sign. We are solving an equation. So the 3x I'm going to leave alone, but I'm going to distribute that 2x. 2 times x is 2x. 2 times 1 is 2. So I can finish solving this by subtracting 2x from both sides. So I'm going to get 1x equals 2. That would be the solution to that problem. We are going to skip part D for a moment. Sorry, part C, and look at part D because they're pretty similar. What I want to point out about this one, there's no distributing, but there is an x times an x. People mess this up a lot. The main thing people aren't sure is x times x 2x? Or is x times x x squared? My remedy for this, pick a number and see which one seems to be correct. So is 3 times 3 the same as 2 times 3? Or is it the same thing as 3 squared? Well, 3 times 3 is 9. Which of these turns out to be 9? The one where you're squaring. When you multiply a number by itself, it's the same thing as squaring that number. So that means on this problem, when I do x times x, we get x squared on one side of the equal sign. On the other side of the equal sign will be 4 times 12, which is 48. So the frustrating thing about this one, unlike the others, where yes, we had to worry about a negative, yes, we had to distribute, for this one, we have a quadratic. This one, we're not going to try to factor because what I want to point out is we almost have x by itself. That squared is the only issue. And to undo a squared, just like the Pythagorean theorem, we can square root. The directions do say simplest radical form. So I'm going to take that and I'm going to break it apart. I'm just going to look for any numbers that divide into the 48. There should be a whole lot of 2's and eventually a 3. So there should be 1, 2, 3, 4 2's and a 3. Everybody else broke down. So I'm not sure how your teacher might have been writing it, but you could rewrite it like this. But remember, we're looking for pairs of numbers. 2 times 2 is 4. The square root of 4 is a regular 2. So this 2 comes out of the radical. This 2 comes out of the radical. And we're still multiplying numbers together. Leftover numbers stay in the radical, meaning our simplest radical form answer is 4 square root 3. And then you should get out a calculator and type it in. Nearest tenth means one number after the decimal point. Again, stupidly, I didn't bring a calculator, but I am fairly certain it's either 6.8 or 6.9. Don't quote me on that as being exact. It might be 6.8, but it should be close to that. So we've been doing we've been doing proportions that turn out to have factoring. Those will keep coming up again, but for now we're going to stick with this and we'll practice more of that tomorrow. I do want to jump to number 3. The other main thing you're going to see with this are these word problems like scenarios. So this says a scale model of a car is 1 inch to 2.5 feet, which means if you made a model and you made it 1 inch wide, in real life it's representing 2.5 feet. Anytime we give you one of these ratios already, pretty much always, unless it asks for the ratio of something, use it in a proportion. I'm going to use the 1 inch to 2.5 feet. To which you may be saying, wait, I thought you said we can't have different units. We have to reduce it. That is true if you have a ratio and that's your answer. This question doesn't say, what is the ratio? It wants to know, how big is it in real life? So if I'm trying to answer a how big is something in real life, I'm okay mixing units until I get to the end when I'll have a united answer. So right now, again, this is putting a model distance or size over a real life one. The main thing about proportions is they have to be equal, meaning you have to keep putting model over real. So when I go to read this part here, the wheel on a model is 0.75 inches. I have the model up top currently, so I'm going to put 0.75 inches on the top, which is okay because I'm not trying to make inches cancel out. We are not doing a unit conversion. I'm trying to say these fractions are equal. So I'm going to put it over x because I don't know its real life distance, but I can find it because we now have a proportion that we know how to solve. So what I want to point out before I go to solving this currently has inches over feet. So when we get done with this one, it's going to have to be inches over feet as well. So this answer will be in terms of feet. So I'm going to ignore my units from here on out because I've already addressed them, and I'm just going to cross multiply. X times 1 is x. And 2.5 times 0.75. Oh, do I not have a calculator on here? Ugh. Man. Sorry guys, I am really unprepared. This is going to be some number. I don't know what it is. I'm not prepared. My bad. Get a calculator, type it in yourself, put that answer here. We're going to do the same process again for this problem. I'll probably not be able to do the whole thing again because, again, I don't have a calculator. However, I'm sticking with that order of model to real because this was the initial information. I'm going to keep utilizing that. So I'm going to keep putting the model 1 inch over the real life 2.5 feet because I'm trying to find the width on a model. So I don't know this model length or width, whatever. The actual door, though, the real life door, I know that. Sorry. So I'm going to put the real life model of 3.5 feet here. It's always helpful to have the units because now I can see here I have inches over feet, which has to be equal over here because, again, we have a proportion. So this answer is going to be in inches. When you cross multiply in this one, you're going to get 3.5 times 1, set equal to 2.5 times x. So to get x by itself, we will have to divide by 2.5. 3.5 divided by 2.5 is 7/5. So 1.4, I think. I'm guessing it's 1.4. But again, the correct answer can be found by actually doing the division. I just didn't do the division. That's a lot of what you're going to see for these problems. So yes, you'll get some just solve this proportion. Yes, you'll get some reduce this ratio, but you'll also get these word problem type scenarios. So turn the page. Let's do one more. I'm trying to think of a good one to do. Let's look at number 7. Eloise is making a model of a Ferris wheel that is 60 feet tall. The model is 15 inches tall. Eloise also is making a model of the Sky Needle ride that's 100 feet tall, and she's going to use the same scale. How tall is the model? So we have this scenario where we're taking something and shrinking it down to a model. I'm going to still use that same setup we started with model over real life. Now, I will say you don't have to do that. You could do real life over model, or you could do Ferris wheel over Sky Needle. There's a lot of ways to correctly set up a proportion. This is just the way I'm going to choose to do it. So for the Ferris wheel, I know the model is 15 inches. And I know the real life one is 60 feet. Not reduced, but I'm not done with the problem, so that's okay. I'm going to write another fraction that is still model over real. Since it's using the same scale, it will still be equal. I will still put the model, which is the question I'm supposed to be answering, to real, which is in feet. So I'm seeing that I have the units the same. Inches over feet is going to end up with something over feet, meaning my answer will be in inches. So just cross multiply. 60 times x is 60x. 15 times 100 is 1500. And I'm going to divide that by 60 to solve. So that's going to be 25. Yes? I think it's 25. So 25 inches would be the height of the model. There are more examples on here. There's more that we'll do tomorrow, but for now that should get you a start. There's an online assignment from the online textbook, so give those a whirl. Don't skip all the word problems because you do need practice on it. But remember, proportions have to have everything equal all the way across, and then you're going to solve what's left. When it talks about a ratio, it'll give you the order like this, and then you just have to make sure you keep that order. So keep your order, and then address your units before you reduce.